Well, hello everyone, and good morning or good afternoon, depending on where you are. My name is Nick Klingaman, and I work at the National Center for Atmospheric Science, based at the University of Reading. I'm grateful to the organizers for the chance to record a brief presentation for you today about some work that we've been doing to understand why the Madden-Julian oscillation has improved in the latest configuration of the Met Office's climate model. So for the last several model generations, spanning 10 or 15 years or so, the Met Office's climate model has had quite a poor representation of the MJO. And you can see this here in a Hofmüller diagram for the GC2 configuration, which was sort of the CMIP5-esque generation of the model, where the model shows quite a poor eastward propagation of the MJO relative to what we see in satellite observations of OLR. But recently, the latest Met Office model configuration, GC3, which is the one that will be used for CMIP6, has shown a slightly improved propagation of the MJO, starting from the Indian Ocean and going through into the maritime continent. Still not quite as good as what we see in observations, but a definite improvement over GC2. And so the aim of this analysis was to understand why we've seen this improvement in the MJO, and to understand whether the physics changes that were made between GC2 and GC3, and there were many physics changes, whether those contributed to an improved representation of the MJO, either directly by modifying something about the convective physics in the model, or indirectly by changing the basic state. And some results recently from literature suggest that the basic state can be just as important, if not more important, than the physics for the MJO. So here you can see some of the biases in the basic state that we have in GC2 and GC3. So I'll start with GC2, which is on the bottom. So here in GC2, you can see that around the maritime continent, we had dry biases in precipitation and cold biases in sea surface temperatures, both to the west of the maritime continent and to the east in the western part of the Pacific. And in GC3, instead, these have changed to be warm biases around the maritime continent and a reduced wet bias, and a reduced dry bias, sorry, and an increase in the wet bias in the Western Pacific as well. So now the question we wanted to try to answer was whether these changes in the basic state in the atmosphere and the ocean have led to some of the improved propagation of the MJO that we've seen due to a sort of a moister environment around the maritime continent and warmer sea surface temperatures. So to investigate the role of physics changes for the MJO and for the basic state, we're going to use a model framework that's called the Met Office's Global Ocean Mixed Layer Model. This is something that we've developed here in NCAS at Reading, where we take the same atmospheric GCM that's used for GC3 at the same resolution, but instead of coupling it to the dynamical ocean that's used in GC3, we couple it to many columns of a one-dimensional mixed layer ocean. And this allows us to tinker with the ocean mean state by changing the profiles of the heat and salt corrections that are put into the model to account for the lack of ocean dynamics in the 1D model. And this is a technique that you can read more about in a couple of papers that we've published on MET-UM-GOML in geoscientific model development over the last few years, but unfortunately I don't have time to talk about in this presentation. But we can use this technique to make the ocean mean state in GOML mimic either an observed climatology, a coupled model climatology, or some hybrid of the two, where we can impose one basic state in one basin and a different basic state in another ocean basin. So we've run 5 experiments with this GOML model. One where we use the observed climatology globally, taken from 30 years or so of ocean observations. One where we run with the GC3 ocean climatology globally, one where we run with the GC2 climatology, and then 2 simulations where we blend the two, and we use GC3 either in the Indian Ocean or the Pacific Ocean, while we use the GC2 climatology in the other ocean basins. And if we look at the MJO that's represented in these simulations, at the top here we have just the standard GC3 and GC2 as was shown on the previous slide. And then in the middle and bottom rows, we have the 5 experiments that we've performed with GOML. You can see that when we use the observed ocean mean state, we have some ability to represent eastward propagation, but it's not as good as we get it's not as good as we get in GC3 for sure. When we run with the GC3 ocean mean state globally, we can see a greatly improved propagation, which suggests that the GC3 biases that we saw in those SSTs are helping to improve the MJO propagation through the maritime continent. By contrast, if we use the GC3 atmospheric model, but with the GC2 ocean mean state, the MJO propagation degrades quite a bit, though it is still better than the standard GC2, and this suggests that the physics changes to the atmosphere between GC2 and GC3 had some effect on improving the MJO. If we impose those GC3 biases regionally, we can see that in the Indian Ocean case or in the Pacific case, we improve MJO propagation a little bit, but just local to the region where we imposed the GC3 ocean state. So I'll leave you with the key message here and the summary points, which is that model physics changes can affect the MJO not just through the physics of the MJO itself, through altering the convective physics, but also through the effect of those physics changes on the MJO basic state, or on the atmospheric basic state on which the MJO operates. And we've seen that here when we've compared GC2, which had quite a poor representation of the MJO, to GC3, which had a better one. We showed that that was primarily by the changes in the mean state between those two model configurations. So thank you very much for your attention, and I'll be very happy to take any questions or discussion via email. Thank you.